Hello and welcome to 10th lecture in our 19th chapter in a comprehensive course on AI, ML and DS. Now we want to talk about this concept, posterior probability or Bayes theorem, which helps us to calculate the probability of event A given that event B has already occurred, or that means it is probability of B given A multiplied by probability of A divided by probability of B. Okay, so that equation is called Bayes theorem. We will not go into the proof of it and all that, but we are more interested in how it will apply to our various cases of data science and in general also in various real life situations. So this probability of A given B has already occurred. That probability is different than this probability of A. Okay, this is called simple probability. But probability of A given B has already occurred. That is not the same as absolute probability of A. This is the absolute probability of A. Well, this I can call something like relative probability of A. Okay, so this is absolute probability of A. For example, here, if I call that first time I have tossed the coin and I got that I got one tail. Okay, so that means one event occurred. That is B event has already occurred. Now next time I toss the coin, then what is the probability of getting head? Now there are two approaches to do this. If the instruction says that treat each experiment as one individual independent event, then in that case next time also the probability of getting head would be 1 by 2. But suppose it is given that the whole 2 times coin tossing that you consider as one experiment. Okay, so that means first time coin toss I have done and I got tail, but that my event is not yet completed. I am doing second coin toss, and then what is the probability of getting head? Now that means it is probability of getting head given that previously a tail has already occurred. Okay, so that type of probability is here. Okay, probability of A given that some other event has already occurred, and most of the time this head and tail was not a good example, but A and B, two events should be relatively independent or unrelated from each other. Okay, head and tail are related with each other, right? But two events should be independent of each other or unrelated with each other. So let us take one example. But how to remember this equation? Then P A by B is equal to P B by A multiplied by P A divided by P B. However, by does not mean division. That much you have to remember. Okay, it is actually P A given B equals P B given A multiplied by independent probability of A divided by independent probability of B. Okay, and independent probabilities are found by that thing, number of favorable outcomes divided by number of all possible outcomes. So these two are, that means easy to find because we have done that example of coin and die and so many other examples in previous lecture. Okay, so we know that this absolute probability or simple probability PA and PB, they are easy to find. The issue is this only. And what Bayes theorem says that if you somehow cannot find probability of A given B, but if you are given probability of B given A, then use that probability of B given A and just multiply it by simple probability of A, and that is the simple probability of event which occurred here initially on the right side of equation divided by simple probability of B. Okay, so that equation is called Bayes equation. Now let us take one example, then only it becomes clear. So this is one simple one line statement. A test for disease is 95% accurate. Now what is the meaning? If the test says that you have the disease, then that means there are 95% chance that you actually have the disease. But there are 5% chance when the test will be positive, but you don't have the disease. Okay. Now only 1% of the population has the disease. Each sentence you have to read as the independent sentence. So this sentence has nothing to do with the previous. So that means if I take any random sample from my population of 100 people, then there is only 1% chance, or there is only chance of one person having that disease. 1 in 100 has a chance, probability that they are having the disease. If the test is positive, then what is the probability that the person has the disease? Now this is different, that you should understand that we say that only 1% population has disease, or that means the probability of having the disease is 1 by 100. But here also they are asking what is the probability that the person has disease. So will that be 1 by 100? No, because here we are asking that probability when some other event has already occurred before that, if the test is positive. So that means that will not be 1 by 100. 1 by 100 is the absolute probability that if I pick up any random person from my 100 persons, then he has the disease, then that probability is 1 by 100. But now if I take a sample of all test positive people and then I pick up a random person out of them, then what is the probability that that person has the disease? So that means test is positive, that event has already occurred. Okay, and now I am asked what is the probability that the person has the disease. So this is the thought process. We always start with Bayes theorem. How we will write this with whatever is asked? Probability of disease given that test is positive, correct? So probability of disease given that test is positive. But that I want to find. So probability of disease given that test is positive is equal to probability of test being positive when the person has when it is given that the person has disease into absolute probability of disease divided by absolute probability of test being positive. Try to understand, and I will now open this image and you will become clear. So this is the thought process. You are asked this: if the test is positive, what is the probability that the person has the disease? So probability of disease given that the test is positive, that means you have collected a sample of 100 people who all have tested positive, but testing positive does not categorically mention that that means that the person will have disease. Why? If your test would be 100% accurate, then that would be a different thing. But your test is also having some inaccuracy, right? And as a result of that, even if I have a sample of 100 persons who have who have tested positive, then I cannot say that all of them will have the disease. So that is what they are asking, that if a person has tested positive, then what is the probability that the person has disease? So that means probability of disease given that person has tested positive. Are you getting it left side? That is what we want to find. But Bayes theorem says that if you cannot find this, then try to find this. Probability of positive, so that means these two you have to interchange. Probability of positive given that person has the disease. Here you want to find probability of disease given that person has tested positive. Here probability of testing positive given that the person has the disease multiplied by absolute probability of having the disease divided by absolute probability of testing positive. Okay. Again I am speaking. Probability of having the disease given that the person has tested positive is what you want to find. But instead of that, Bayes theorem lets me find this, and that will be the same. So that is probability of testing positive if the person has the disease multiplied by absolute probability of having the disease divided by absolute probability of testing positive. Okay. Now next step would be, so that means instead of finding this LHS, which is the probability of disease given that the person has tested positive, I can find the three terms on the RHS and use them, plug in them in this equation. Now when I want to plug in them, I have to think about, are these all three readily available? So think that what are given to you. So if you think properly, then this test is 95% accurate. That means if it is used for a person who already has the disease, then it will test positive for 95 out of 100 persons. So that isn't that these things, probability of being positive when the person has the disease. I think you are getting it, that the test is 95% accurate means if I take 100 people who have the disease, then my test will correctly identify 95 out of 100 people as yes, they have the disease. So that means my test will also give positive result. Okay. So at least one term I am given to. Now this term, probability of disease, that is absolute simple probability. So isn't it this thing? 1% of the population has the disease, right? So that means that probability of having the disease is 1 out of 100. Okay. So that means that also is given to you. But these things, probability of being positive, now that is not given to me. That what is the absolute probability of being positive? So at least find out what is given to us. So we are given this thing. Test is 95% accurate means probability of test giving positive result when the 100% have the disease is 95 or 0.95 out of 1, or that is 95 out of 100, right? Also I am given 1% of the population has the disease. So that means probability of having disease in the entire population is 1%, or that is from 100, 1, or from 1, 0.01% has the disease. Okay, but I know that whenever two mutually exclusive options are there, like head and tail, then the sum of their probability becomes 1. Head also has 50% in the coin toss example, and tail also has 50%. So here probability of having disease is 1%. So obviously probability of having not having disease, that is 99%, right? So I am given probability of having disease. So indirectly I am given probability of having non-disease also, because the sum of these two should be 1. Okay, these are simple probabilities. Then I am given a test for the disease is 95% accurate. So that is probability of test giving positive result when the person actually has the disease is 0.95, or that means if there are 100 persons who are actually having the disease, and if you use your test for verifying that, then my test will say that yes, 95 out of 100 have the disease. But my test will fail for 5% of the people because all 100 were having disease. But my test have accuracy of 95%, so that is why it will fail. So probability of my test giving positive result when all 100 are having disease is 95%. Okay, correct. And So from that also I can find another probability. That probability of my test giving positive when the person has no disease. That is all. That is 5% because my test is 95% accurate. So that means my test is 5% inaccurate. So if I take a sample of 100 non-disease persons, then also my test will give positive test that the person has disease for 5 out of 100. Okay, because the accuracy of my test itself is 95% or the error in my test is 5%. Is that clear? So I am given first this term P positive disease. Okay, that is this. I am given P disease, this term. I am not given the term in the denominator, but instead I am given two extra terms. That is this. Actually, I was not given that, but I calculated because the sum of two related probability should be 1. Similarly, this is also sum of two mutually exclusive related probability, that should be 1. Okay, so that is why I calculated this and I calculated this. So unfortunately, I do not have this, but fortunately, I have some extra things apart from first and third term, which are required in my equation. I have some extra things: P no disease and P positive no disease. Okay, this 0.99 and this 0.05. These two extra things I calculated because the total probability of mutually exclusive events, the sum of their probability should be 1. So now we are thought process step 3. Okay, so can I think what term in the Bayes theorem is not available and what extra terms do you have? So that I already explained that this term in the Bayes theorem P positive is not available, and which extra terms I have, then P no disease, a simple probability of no disease is 0.90. That is okay. That is simple probability, but P positive disease, I think here I have made some mistake. Okay, so actually P no disease, whatever I calculated by that sum should be 1. That is the extra term P no disease, because you can see here P no disease is required anywhere, so no, it is not required, right? And similarly P positive no disease is required anywhere, then no, it is not required. Okay, so I will make the correction and then continue the recording. Just a second. Okay, so the correction is done now. So this term, simple probability of not having disease, is 99%, because it is given that only 1% of the population has the disease. So that means 99% of the population does not have the disease. And this term is also extra, P positive no disease, or that means that the probability of testing positive even when the person is not having disease is 5%, because my test itself is having 5% error. 95% accurate means 5% error. So if I take 100 persons who do not have disease, still my test will give false positive for 5% of the cases. Okay, so that terms are extra. So now this term is not available to me, which I require here, but these two are available. So now my goal should be what? Somehow can I find this term which is not given to me using these two terms which are extra. Okay, so yes, I can find, and for that this is important step, so please pay attention. This step says that I want to find this term which is not available, P positive, then I can write it as P positive disease. So that means probability of test giving positive result for a sample of people having the disease multiplied by P disease. Now this is here actually not a division, but you can mentally consider this to be a kind of division. Okay, and P positive no disease. So that means if you take a sample of non-disease people, then your test giving a positive. So this is sample of disease having people and your test gives positive, means this is true positive. So that is your test is giving correct result. But this is false positive. Sample was having no disease, but your test is giving positive result multiplied by P no disease. Now how this equation is written? Try to understand. Mentally think that this is P positive divided by P disease. Mentally multiplied by P disease. So P disease will be cancelled. Similarly, mentally think that this is P positive divided by P no disease and multiplied by P no disease. So then in that case P no disease and will be cancelled. So what will be this P positive when disease is there, and what will be this P positive when no disease is there, right? Because on this side the situation is disease situation. That is, you have seen that this whatever absolute probability you are using, that is called situation. Okay, so this is the P positive when disease situation is there, and this would become P positive when no disease situation is there. So if these two are also exclusive, test being positive when disease situation and test being positive when no disease situation, so then that sum should give P positive total positive probability. Okay, that will not give 1, that you should understand, because that is what you are trying to find, and these two do not cover all possible events. So then you have to find this P positive disease. Now what is the meaning? Take a sample of 100 diseased person and test them and find the probability that your test gives correct result. But that is already given that the test gives 95% accuracy. So that means this is 0.95. Okay, multiplied by P disease. So that is absolute probability of having the disease. But that is also given here. Only 1% of the population has the disease. So that means this number would be, P disease would be 0.01. Okay, and this P positive when no disease is there. So that means take a sample of 100 non-diseased person and test them using your test. Then what are the chances that your test would give them as having disease or false positive? So that my test is 95% accurate means 5% of the time it will go wrong. So that means this P positive and no disease, that will be 0.05, correct? And P no disease, simple probability of having no disease. Now that can be found from this sentence. Okay, only 1% of the population has the disease. So 99% do not have the disease. So from that sentence, that is only 1% of the population has the disease, I could find two things. Absolute probability of having the disease, P disease, that is 1% or 0.01, and absolute probability of not having the disease, that is 0.099. 99% do not have the disease. Okay, and this two left side, P positive given disease and P positive given no disease. From which sentence I found them? I found them from here. Okay, a test for disease is 95% accurate. So that means given that the people have the disease, okay, given that the people have the disease or entire sample of 100 have the disease, my test will correctly detect them, true positives, correctly detect them as having the disease in 95% of the time, or 0.95. And this says that, this other left term, so that says that P positive for no disease. That means take a sample of 100 people having no disease, and how many times my test will falsely give them positive having disease. Then my test is 95% accurate means 5% inaccurate. So 5% of the time it gives that false positive. Okay, so then this term gives this. So first sentence I'm spending so much time because this should become very clear. So first sentence gives me this left side term, this term, P positive given disease and P positive given no disease. Okay, and this sentence only 1% of the population has the disease, that gives me this absolute probability of having the disease 0.01, 1%, and absolute probability of not having the disease, that is 0.99. And this rule is called chain rule. Okay, so this is called chain rule of probability. Now once I substitute, I got my P positive, that it is forget about the calculation, that you can check that it is correct. So I got my P positive 0.059. My aim was to substitute that value of P positive in this equation because other things were already known to me. So P positive given disease. So the chance that my test will give positive when the sample of 100 people have the disease. So that is 9.95. So the numerator has 0.95 as the first term. Then P disease, that is absolute probability of any one person randomly picked up from the population having the disease. Then 1% of the population, so this is 0.01, and divided by P positive, which I just now calculated using the chain rule, that is here 0.059. Okay, so that means 0.95 divided by 0.059 multiplied by 0.01. Okay, so that would be 0.95 divided by 0.059 multiplied by 0.01. And if you find it, then this would be roughly 16% probability. Now this leads to some very important insights. This leads to that insight that why doctors insist on multiple different tests before categorically saying that you have the disease. Because here what was the situation? You tested positive. Okay, you tested positive and you got that 16 so is it the time to scare the patient that you tested positive means you have the disease? And think about the situation if it is a disease like cancer or AIDS. You have the disease, you start treatment. No, because even if he tests positive, if the chance of that disease itself in entire population is just 1%, then even after testing positive, the probability that the person actually has the disease came out to be only 16%. So that means there are still 84% chance that a person may not have the disease even after he tested positive because of inaccuracies in the test process itself. And as a result, for same disease, multiple different tests exist. So second test you will be conducting, then third test you will be conducting, fourth test you will be conducting, particularly when it is AIDS or cancer or that kind of serious disease. And then after that, you will add the probability given by all tests. That also which probability, not simple probability, but this kind of posterior probability, that if all tests come positive, then what is the probability that the person has disease? And if one came out to be 16%, another came out to be 23%, another came out to be 25%, and another came out to be 18%, and the sum of all that came out to be greater than 70%, 4 tests. Now you can tell your patient with surety that yes, you have the AIDS or you have the cancer. So next time when your doctor asks for multiple tests, before you scold your doctor, please understand the probability and the complexity of mechanism. Okay. So this is one thing. I still want one small discussion. So just pausing for a second recording and then continue. Just a quick revision of this whole discussion. This much only one sentence was given to us. A test for disease is 95% accurate, full stop. Only 1% of the population has the disease, full stop. If the test comes out to be positive, what is the probability that the person has the disease? So from test for a disease is having 95% accuracy, I got these two things. That if there is a sample of 100 diseased person, then the test will also give positive result in 95% of the cases. And if there is a sample of 100 non-diseased person, the test will still give positive result in 5% of the cases because it has 5% error. Correct? So red goes to these two red arrows. And those two red terms are going on either side of this plus symbol in that equation, right? So one, P positive when the sample is of diseased person is 95.95, and here another term, P positive when the sample is of non-diseased person is 5% because that is erroneous positive, false positive. So true positive and here false positive. They go on either side of this positive symbol. Okay. Now the next sentence I have to read, which is easier. Only 1% of the population. This term is important. So 1% of the population has the disease. That is the absolute simple probability. Whenever you read the word population, that is absolute simple probability. So that means if I take 100% randomly from the entire population, then 1% will have the disease. So disease with probability, simple probability is 0.01. And that means 99% will not have the disease. So the non-disease probability is 0.99. So these two blue terms, so that is blue arrow terms, they also go on either side. Two simple probabilities go on either side, and two posterior probabilities, they also go on either side. So when I said that P positive divided by disease and P disease is cancelled, please do not understand it that way. That is just a way of remembering the thing so that if you forget this equation, okay, this is not that division, this is a posterior probability. Okay, the only thing is that the original posterior probability which was required to me, that is this, that probability was not given to me. While this probability, posterior probabilities which I am using, this, they are given to me. So that means for this there is no need to use Bayes theorem. They are already given to me by that blue arrows, that they already red arrows, they already take me to first posterior probability on the left side of this plus sign and the next posterior probability on the right side of that. But for the sake of understanding, you can write it this way, that P positive disease multiplied by P disease and P disease is cancelled, just for the sake of understanding. It is completely wrong, please. But then this is called P positive for disease situation, and this is called similarly here P positive divided by no disease multiplied by P no disease, and you can say P no disease is cancelled. Again I am saying that is completely wrong way of saying, but you can say that then what will remain if these two are cancelled, then only P positive will remain, but that is P positive for non-disease situation. Okay, and that means these two are not that type of event which are mutually exclusive event, and therefore their sum of probability should be 0. So the left side of that plus sign, that is P positive for the disease situation, and the right side of that plus sign, that is P positive for the non-disease situation, but they are not mutually exclusive options. In other words, that being positive does not depend only on being positive in test, does not depend only on whether person has the disease or whether person does not have the disease. If it would be that simple, then the sum of these two, when I do the sum here, that would be 1 only. But it is not that simple. Why? Because being positive depends upon the disease, whether or not person has the disease, but it also depends upon chance. Because the test to detect positivity, that is itself having some inaccuracy and that error. So now you should understand why we require the concept of that posterior probability or probability given some event occurred. So that means two independent events are occurring here. One, from population you are picking one person and there is a chance that that person has the disease. But other chance also is coming into picture. That other probability is also coming into picture. That your test itself has only 95% probability of being accurate and it has 5% probability of going wrong. Okay. So I hope that now this thing is clear. Okay. I should do one thing, that I will paste this diagram in the Jupyter notebook also, and then you will get that Jupyter notebook. So it will remain a good memory of what I am talking about. Okay. But remember that the division thing, that this is P positive divided by P disease, and this is P positive divided by P non-disease, that is just for understanding, just for remembering the equation. Okay, otherwise this is posterior probability of testing positive for a given sample of 100 diseased person. That is right way of saying. And this is the posterior positive probability of testing positive for a 100% sample who do not have the disease. So this is 90.95 because it has 95% accuracy, and this is 0.05 because it has 0.5% error. Okay, so please understand things properly. I will paste this in the Jupyter notebook, and we will see the next problem in the next lecture.